Hi everybody, I've had a request to work through the 2017 NZQA electricity paper, and the question was question 1. Can get that to send back. So I'm just going to read through the question so that you can see what I'm talking about. So this is about electrostatic speakers, and the sound is produced by moving a diaphragm, which is actually just a thin sheet of polyester film between two conducting plates that are 3 centimeters apart. So the plates are shown over here, and I've drawn the diagram over there. They're connected to a 6 kilovolt high voltage DC power supply. 6 kilovolts is 6,000 volts. And so the first question was to show the electric field strength, which is 2 times 10 to the power of 5 volts per meter, which is 200,000 volts per meter. And then so the initially neutral diagram is placed centrally between the plates. So that's the green line is the diaphragm. But the thing is, the diaphragm can only move a total distance of 1 centimeter. So that's marked, and that comes later on. And now that's charged by adding a whole lot of electrons onto it. So you see that it's got these negative charges. And then question C is the uniformly charged diaphragm is fixed at the top and the bottom to smooth frictionless sliders, which only allows the diaphragm just to move a little, not all the way, not 3 centimeters, but this way. And then it says, explain why the size of the force on the diaphragm remains constant and no bending occurs as the diaphragm moves within the sliders. So they're asking why the force remains constant, and as a result the thing doesn't sway like this but just stays straight. So the thing is, because you've got two parallel plates which have opposite charges, the field between the plates is a uniform electric field. That means the strength of the field is the same at every part between the two plates, and because the electric field strength is the same, the force experienced by charged on the diaphragm is the same. So it's like if you had a strong gust of wind blowing from this side, the plate would move or bend like that. But if you had a gust of wind from this side and an equal and opposite gust of wind from the other that's experiencing a force, it would stay where it is. So the forces on both sides are equal, okay? So that's why it stays the same. So size of the force is a constant because electric field strength is a constant. So that's the answer to question C. And then question D is a calculation question, but there is some data given to us. So what they said is, at one point, the stationary diaphragm has a uniform negative charge of, there we go, I tried to do some things over here, has a uniform negative charge, that's my Q. So that's a charge on there, is negative 4.20 times 10 to the power of negative 5 coulombs. And it's initially located in the middle of the slider. So this whole slider is just 1 centimeter. So if it's in the middle of the slider, the most distance it can move is 0.5 centimeters. We just have to keep that in mind. The mass of the diaphragm itself is 5.80 times 10 to the power of negative 5 kilograms, and the conducting plates. So the distance from one plate to the other is 3 centimeters, and the distance the diaphragm moves is just between those. Okay, we have to find the maximum speed the diaphragm will move before it is stopped by the edge of the slider. The slider is here. So in order to find maximum speed, the implication is kinetic energy. When you're thinking about energy, you're looking at work done, and the work done has to do with force multiplied by distance. Okay, so the first thing is, in order to find the energy, you got to find the work done, which is force times distance. And now, how do we get the force? So for an electric field, force is E times Q, where E is the electric field strength, which we found earlier was 200,000 volts per meter, and Q is the charge, and the charge is 4.20 times 10 to the power of negative 5 coulombs. And if you want to find the work done, which is F times D, I'm just going to add the D here. So all in one step. And the distance the slider moves, it's only 0.5 centimeters, which is 0.005. So when you multiply all this, you end up with, it's gone, okay, you end up with 0.042 joules. Okay, so that's the work done. Now this work done is converted to kinetic energy, which is half mv squared. So your half mv squared is 0.042 joules. Now the mass is the whole diaphragm is moving, so you got to take the mass of the diaphragm. So my v squared is 2 times 0.042 times the mass of the diaphragm, which is 5.80 times 10 to the power of negative 5. And in order to find v, I got to find the square root of that. So when I put all that in my calculator, I get 1448, and square root of that is 38.05 meters per second, which is the same as 38.1 meters per second. So I hope that was clear and you understood. Bye for now.